So we're continuing to look at the AIME problems, the AIME II problems from 2012. This is question 8. Once again, if you don't have the questions with you, pause it and read the question. Maybe try it yourself before you go on and you can hear my solution. So we've got two complex numbers and we've got these two equations. It is actually possible to eliminate a variable and get it in terms of one of these two variables and then solve a quadratic equation that you get for that variable and then go back and find the other one, and it could be done. But I think it's a lot simpler just to multiply the two equations together. And what's kind of cool about that is when you do the multiplication, and you have to remember either the FOIL method or more generally how to multiply sums together like this. But most of the terms actually, the variables cancel. You get a ZW term when you multiply the Z of the first term times the W of the second term. But then when you multiply the 20i over W by W, the W's go away. And when you multiply the 12i over Z by Z, the Z's go away. You're left with 12i. And then the last term on that side is, 240i squared over ZW. Great. And similarly, when you multiply at the other side, it's just the standard old thing. You wind up with, once you've simplified and gathered the terms together, just ZW plus 32i minus 240 over ZW equals, well, it works out to be negative 30 plus 46i. And you can put it all on one side. And what's really cool about that is then if you multiply both sides by ZW, you get a quadratic equation in ZW, right? ZW squared plus a complex number times ZW plus, well, 240 minus 240 equals 0. We can solve that if you don't see how to factor it right away, and maybe you do, but I sure didn't, so I used a quadratic formula. I mean, it's a little bit yucky. I'm not thrilled about it, but it's perfectly doable. I mean, now I just have negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And now I just have to do a little complex arithmetic. Well, first let me do some simplifying if I can. I mean, this is just, I factored out, for example, I want to factor out of the square root, make the numbers smaller. If I'm going to have to do this without a calculator, I might as well make the numbers smaller. So I see that the 4 times 240, well, if I can factor factors like out of the 30 minus 14i, well, they're both divisible by 2, so I can factor a 2 squared out of that, which is another 4. And then ultimately, when I factor that out of the square root, it'll be a 2. And now I can divide everything in the numerator by 2, and it's going to be a little easier, right? At least now I don't have the fraction anymore. And I've been putting it off. I can multiply 15 minus 7i quantity squared. I get 225, and then minus 2 times 15 times 7, so that's 30 times, that's 210, minus 210i, and then 49i squared. I'm going to be subtracting 49 from everything, and then the plus 240, and again, I have to do it. I have to just do the arithmetic. So ultimately, I get 416, right? 225 plus 240 is 465, but then when I subtract the 49, it's 416 minus 210i, and somehow, if I'm going to evaluate this thing, or at least figure out which one gives me the biggest absolute value for ZW, which is, after all, what the problem asked me for, I'm going to have to take that square root. Well, I strongly suspect that 416 minus 210i is going to be a perfect square. If this is going to work out at all nicely, I'm going to need that to be a perfect square, complex square. So I need some complex number, a plus bi, that when I square it, I get 416 minus 210i. That sounds pretty nasty, but if things are integers, it's probably not too bad. When you square a plus bi quantity squared, you get a squared plus 2abi plus b squared I squared. So that's the a squared minus b squared is the part that doesn't have any i's in it anymore, and that's 416. And the 2abi has to be 210i. Well, actually it has to be negative 210i. Let me fix that. There, that's better. So ab has to be negative 105. So AB has to be negative 3 times 5 times 7. And since A squared is going to have to be bigger than 416, A has to be bigger than 20. So it's either 21, I mean absolute value. And it really doesn't matter whether we let A be positive or negative, because ultimately we're going to do a plus or minus the square root. But we'll get to that later. For the moment, if A is positive, A has to either be 21 or 35, or I guess it could be 105. But it doesn't take much to see that 105 is ridiculous. Then b would have to be plus or minus 1, and a squared would be 10,000. That's way too big. In fact, the one that's jumping out at me is if a is 21, so this means that 21 squared minus 5 squared, well, 21 squared is 441, and that's just 25 more than 416, so it really works perfectly. We're done. And of course, it could be 21 minus 5i quantity squared, or it could be negative 21 plus 5i quantity squared. Those, if you just multiply 21 minus 5i, the whole thing, by negative 1, you get the other one, and when you square it, it doesn't matter. But that's why we've got a plus or minus the square root in the problem. So either way, we get two possible values for ZW. Either ZW is negative 15 plus 7i plus the quantity 21 minus 5i, which is 6 plus 2i, or it's negative 15 plus 7i minus 21 plus 5i, minus the quantity 21 minus 5i. Same thing. Either way, that's negative 36 plus 12i. And as you may remember, the problem asked us for the smallest possible value of the absolute value of ZW squared. So if you go back to these guys, the absolute value of ZW is the square root of, well, in one case it's 36 plus 4, right? 6 squared plus 2 squared. In the other case, it's the square root of 36 squared plus 144, which is much bigger. So the smaller value of the absolute value of ZW is the square root of 36 plus 4. And of course, ZW, the absolute value squared, is just 6 squared plus 2 squared. That's 36 plus 4. So the answer to the question is actually 40. Okay, here's question 9. So we've got these two ratios, sine x over sine y is 3, cosine x over cosine y is a half, and then we want to figure out what sine of 2x over sine of 2y plus the cosine of 2x over cosine of 2y equals. It's got to involve double angle formulas, some way. If you don't know that kind of trigonometry, I think this would be pretty much an impossible problem to do. Well, there's one part of it that we can do, even before we know anything else. I mean, one thing's pretty clear. You've got sine of x equals 3 sine y. I just multiplied out the fractions because this way, when I square both sides, I know that the sine squared of x is 9 times the sine squared of y, and the cosine squared of x is a quarter of the cosine squared of y. And I also know the basic Pythagorean relationship that for the same angle, sine squared of that angle plus cosine squared of that angle equals 1. So on the one hand, well, sine squared of y plus cosine squared of y is 1, but also if I write sine squared of x as 9 sine squared of y, and cosine squared of x is a quarter cosine squared of y, the sum of those has to be 1 also. But that's two linear equations. I can, in terms of sine squared of y and cosine squared of y, I can solve for those two variables. I find it convenient to multiply the first one through by 4. I'm going to eliminate the cosine squared now because I have these two equations, and I can just subtract. So that means that 35 times the sine squared of y is 3 when you subtract, and of course that means sine squared of y is 33 over 35, and so cosine squared of y is 1 minus that, it's 32 over 35. So how does that help me with the original problem? I mean, you may remember that this was all about trying to find the value of sine 2x over sine 2y plus cosine 2x over cosine 2y. That was the problem. And well, part of it, frankly, I don't even need all of those solutions for, because if I look at the sine of 2x over sine of 2y and just use the double angle formula for sine, well, it's 2 sine x cosine x over 2 sine y cosine y. The 2's cancel out, and I'm left with sine x over sine y cosine x over cosine y. But that was what my problem gave me in the first place. Right? It was sine x over sine y is 3, and cosine x over cosine y is a half. So sine x over sine y is 3, cosine x over cosine y is a half. That part is going to be 3 halves. So I didn't even need all that other stuff. But now I have to look at the cosine of 2x over the cosine of 2y. And for that, I also use a double angle formula. Cosine of 2x, I could have written it as 2 cosine squared x minus 1, or I could write it as 1 minus 2 sine squared x. And I know what both cosine squared of x and sine squared of x are. And I know what cosine squared of y and sine squared of y are. I just chose to use this version of the double angle formula for cosine, but they all work. So it's cosine squared of x minus sine squared of x on the top, and it's cosine squared of y minus sine squared of y on the bottom. Well, remember, we solved for sine squared of y and cosine squared of y. So I know that the denominator is going to be 32 fifths minus 3 35ths. But we also had known that the sine squared of x is 9 times the sine squared of y. Remember when we squared both sides of those equations, the very first thing we did. So once we know that the sine squared of y is 3 35ths, the sine squared of x is going to be 9 times 3/35. And similarly, cosine squared of y is 32/35. Well, the cosine squared of x is going to be a quarter of that. So that gives me the numerator of this cosine 2x over cosine 2y reduction. So now I'm almost done. I know that this is going to equal, I can multiply top and bottom by 35 also, so it's 32 over 4, which is 8, minus 9 times 3, which is 27, and then the bottom is 32 minus 3, so it's negative 19/29. And of course, to finish, we get that the sine of 2x over sine of 2y plus cosine 2x over cosine 2y is, well, we had 3 halves for the first one, negative 19/29 for the second one, so now it's just arithmetic. You wind up, it simplifies to be 49/58. So the answer to the problem was, and that's in lowest terms, of course, because the top is 7 times 7. So our answer is the sum of the numerator and denominator, which is 107.